Hello and welcome to our lecture on deep learning. In the last lecture we have discussed several gating mechanisms, the GRU, the LSTM. Today we want to discuss how to make recurrent neural networks deep. So we want to discuss deep recurrent neural networks. Well, in the case of the perceptron, we simply increase the flexibility of the learned functions by adding additional layers to the neural network. Within RNNs, we first need to decide how and where to add these additional layers, where we want to have extra nonlinearities. There are many options. For example, we could add extra nonlinearities to the gating mechanisms in the network. For example, instead of using a single perceptron in the gates, we could use multiple layers. So we could use a multi-layer perceptron instead of a perceptron in the gates. Generally, this would leave the mechanism of the LSTM unchanged. It would just mean that we're computing nonlinear functions. In some sense, this would make the model more sophisticated, and generally this would make sense if we were to believe that the LSTM mechanism describes some form of universal truth on how latent variable autoregressive models work. Alternatively, we could stack multiple layers of LSTMs on top of each other. This would result in a mechanism that is different, that is actually more flexible due to the combination of several simple layers. In particular, data might be relevant at different levels of the stack. For instance, we might want to keep high-level data about financial market conditions, bear or bull market, available at a high level, whereas at a lower level, we only record shorter-term temporal dynamics. Let's, for this lecture, stick with the second variant. So a deep neural network with L hidden layers could look as follows. Here, each hidden state is passed continuously to the next layer. And at the same time, within each layer, it's passed to the next time step. So at time step t, we have as input a mini batch xt, which for mini batch size n would be an n times d matrix, where d is the number of dimensions of the input. Pass it to the computation of the hidden layer, which for layer little l is an n times h matrix, where h is the number of hidden dimensions, and of course we pass the input to the computation of h1. And after we've computed all of these capital L hidden layers, we pass the last hidden layer to the output layer. HL is used to compute output O. So the output layer is an n by q matrix, where we have q output dimensions. Each hidden layer can have an activation function fl for the lth layer. So these don't even need to be the same. So the hidden state of the first layer, layer 1, uses the input xt as an input. So the hidden state at time point t of the first layer is computed as the first layer activation function f1 of the input and the hidden state of the first layer at time point t minus 1. For example, we might compute a perceptron, so basically multiply xt with a weight matrix, ht minus 1 with another weight matrix, and plug this through a tanh function. In subsequent layers, we use the hidden state of the previous layer as input. So instead of using xt as input, we input the hidden state at the same time point, but at layer L-1 as input, and combine it with the hidden state at the time point t-1, so at the previous time point, but at our current layer L. The output function, g, only takes the hidden state of the last layer, capital L, as an input. So OT, the output, is computed as g of ht at layer capital L. Now, because this model has now capital L layers, we need to choose these hidden layers. So the hidden layers are hyperparameters of this neural network. So remember, hyperparameters are parameters that are not trained during model training, but instead have to be set beforehand. So they can be trained, for example, using a holdout experiment, but we can also try out different combinations of hyperparameters to obtain our best neural networks by monitoring a validation error on a different holdout set. Additional hyperparameters are, as always, the number of hidden units at each layer. And while we called the hidden state just capital H of time point t and layer L, in principle, the components that we can stack together can be anything. It could be a regular RNN, and it would really look like this. But it can also be a GRU or an LSTM, and you would connect them. So basically the output of one layer would be the input to the next layer. So instead of computing an output for layer 1, you would compute actually the hidden state of layer 2. So this already was the gist of the idea, how to construct deep recurrent neural networks. Let's summarize. In deep recurrent neural networks, the hidden state information is passed to the next time step of the current layer and the next layer of the current time step. There, in principle, exist many different flavors of deep RNNs, such as LSTMs, GRUs, or regular RNNs. In principle, there are many places where we could apply nonlinearities, where we could connect multiple layers. At the gating, we can put layers of the whole units together, as we just did in this example. However, initialization of these models requires care. And overall, these deep recurrent neural networks, they require considerable amount of work. You need to set the learning rate right, you need to think about gradient clipping, etc. All these tricks that are used for training complex neural networks to ensure proper convergence. And with this short lecture, I already want to say thank you, bye-bye, see you next time.